Hello everyone. Today we will discuss about heat transfer in various non-flow processes, and we can say first law of thermodynamics for a closed system. So there are the following conditions to apply the first law of thermodynamics for this closed system. First condition is isobaric process isobaric process, and in this process pressure will be constant. So there is no change in the pressure. So we will apply this condition if P is equal to constant, then dP will be 0. Okay. So for the first law of thermodynamics, we can say first law of thermodynamics can be written as del Q is equal to du plus del W. Okay. So as per the given condition, process is isobaric, means constant pressure process is there. So this can be written as del Q suffix P is equal to du plus del W. Okay. Also we can say dPV is equal to P plus V dP. If process is constant pressure, so dP is equal to 0. In this case we can say dPV is equal to P So this is our equation first, and this is our equation second. From equation first and second we can say dQ, so del Q suffix P is equal to W is equal to PdV. So this PdV is equal to D. So here this is du plus this dW is equal to PdV. So PdV is equal to this PB. Okay. So this PdV can be written as dPV. Okay. So now we can take common D. So this can be written as U plus PV. And this term is H, enthalpy. So we can say del Q suffix P, del Q for constant pressure is equal to dH. Okay. So this can be written as mCp dt, because H is equal to Cp dt, capital Cp dt or small cp dt. Okay. So this del Q suffix P will be equal to mCp dt. So this is the variation of heat transfer for a constant pressure process, which is called isobaric process. Now we will discuss about the second condition, isochoric process, means volume is constant. If volume is constant, then dV is equal to 0. So applying the first law of thermodynamics, del Q suffix V is equal to du plus P dV. So this will be 0. then we can say del q suffix v is equal to du, and this du is equal to mcv dt. So finally we can say del q suffix v is equal to mcv dt. So this is the heat transfer for a constant volume process. So third condition is isothermal process. Isothermal process means temperature is constant. Okay. So according to Joule's experiment, for an ideal gas, internal energy is the function of temperature only. So we can say U is the function of temperature only. Okay. So here T is equal to constant, then U will also be constant, or we can say du is equal to 0, or we can say internal energy at the inlet is equal to internal energy at the outlet. Okay. So this is the isothermal process and heat transfer through this isothermal process. So in the fourth condition, heat transfer, if the process is adiabatic, it means dq is equal to 0. So here applying the first law of thermodynamics, dq is equal to du plus del w can be written as, this is actually equal to m r upon gamma minus 1 into dt, because this is equal to mcv dt. Okay, so cv is equal to actually r upon gamma minus 1. So this term is written here. So m r upon gamma minus 1 is cv into dt plus dw is equal to p1 v1 minus p2 v2 upon gamma minus 1 for a polytropic process. So this is the work done in the adiabatic process. So we can say del q is equal to mr dt upon gamma minus 1 plus p1 v1 minus p2 v2 upon gamma minus 1. Also we can say, so here we can say mr upon gamma minus 1 delta t is equal to t2 minus t1. Also we know that pv is equal to mrt, that's why we can say p1 v1 is equal to mrt1 minus p2 v2 is equal to mrt2. So here we can say mr upon gamma minus 1 is common. So here it will be t2 minus t1 plus t1 minus t2. Okay, so here this term is cancelled, this term is cancelled, that's why del q is equal to 0. Del q is equal to 0. So in the case of polytropic process, adiabatic process, heat transfer will be 0. Heat transfer will be 0. So now we will talk about the polytropic process. So condition fifth, polytropic process. So there is no big difference between adiabatic and polytropic process. So actually the n is the polytropic index. So this is the difference of n only. So applying the first law of thermodynamics, we can say del q is equal to du plus del w. Okay, so here this will be equal to mr t2 minus t1 upon gamma minus 1 plus this is equal to p1 v1 minus p2 v2 upon n minus 1. So previously it was gamma minus 1. Here in polytropic process, this is the polytropic index, n minus 1 will be used. So dq is equal to this term. So now we can say mr upon gamma minus 1 is common. Mr upon gamma minus 1 is, so here mrt2 minus mrt1 upon gamma minus 1 plus p1 v1 minus p2 v2 upon n minus 1. So this can be written as p2 v2 minus p1 v1 upon gamma minus 1 plus p1 v1 minus p2 v2 upon n minus 1. So it can be written as p1 v1 minus p2 v2 upon n minus 1 means this term minus this term is changed, p2 v2 minus p1 v1. So this will be minus p1 v1 minus p2 v2 upon gamma minus 1. Okay, so now we will take common p1 v1 minus p2 v2, p1 v1 minus p2 v2. So it will be in bracket 1 upon n minus 1 minus 1 upon gamma minus 1. So this can be written as p1 v1 minus p2 v2, and this will be actually n minus 1 gamma minus 1 minus n plus 1. So this 1 to 1 is cancelled. So this will be actually p1 v1 minus p2 v2 into gamma minus n upon n minus 1 gamma minus 1. So here we can say gamma minus n upon this term gamma minus n into p1 v1 minus p2 v2 upon n minus 1. So this is actually work done during the polytropic process. So this term can be written as gamma minus n upon gamma minus 1 into W polytropic. Okay, so heat transfer del Q is equal to gamma minus n upon gamma minus 1 into work done in the polytropic process. So finally we can say del Q is equal to gamma minus n upon gamma minus 1 into work done in polytropic process. Okay, so thanks for watching this video. All the best.